really understand what it truly is today, but we have to get there in steps. And so this lunch and learn is going to be in four parts. First, we are going to go through the history and quick timeline of AI. We are then going to look at several branches of AI and how they have evolved over time. We will then focus on what AI is today. So when people say AI, what do they really mean? And finally, the most important, how are we doing AI within XYZ? Cool. So let's start with the history and let's go back in time, long, long ago. So if we think about the history of humanity, we have had stages of development. So first we sorted safety to not get killed by animals around us. So we built like a lot of tools. We invented fire and so on. With tools, we also kind of started our journey towards laziness. So I believe laziness is a huge motivation for uh, development. So that was our early times of um, achieving laziness. And then we had the cognitive revolution, where we kind of started developing language, maybe not the languages of today, but some kind of language to interact with each other. And then we sorted food, which you guys are eating now, and I'm not. Not to forget about laziness. After the agricultural revolution, we had the industrial revolution, and I call it the peak laziness. So we basically wanted to get rid of anything that we have to do with our hands, with our bodies, with anything that involves motor skills. So we have been inventing machines for everything. And then our quest moved from laziness to boredom. So in one way, AI is our quest towards boredom. We basically not only want to replace things that we can do with our body in terms of motor skills, we also want to replace anything that we do with our minds with machines. So not only do I want a telly to watch something as opposed to watching a real scenery, now I want something to tell me what I should watch versus what my siblings should watch versus what my parents should watch. So I just want to do nothing, right? And that's the quest of AI. And also in this picture, we have I don't know, I'll let you decide if it's gloomy or what, picture of future where we are going to go even deeper inside us. And so that's the future. But again, going back to where we are today, in my opinion, the AI revolution kind of began somewhere 50, 70 to 80 years ago. This is contentious because there is a page on Wikipedia. Could we remove this pop-up somehow? This might mess up the rest of it. Never mind. So there is a page on Wikipedia called Timeline of Artificial Intelligence, and that starts with antiquity, and it has some hilarious references such as someone claiming to have created artificial man out of magnetism, sperm, and alchemy. So I don't know how much credit to give to this. I will stick to my timeline, which is the following. I would say the earliest signs of what we know as artificial intelligence today came around 1950. Sir Alan Turing, everyone might have heard about him. He invented something called a Turing test. Back then, it was called machine intelligence and not artificial intelligence. And so that didn't age so well because just 1 year ago, ChatGPT broke the Turing test. It doesn't mean that we have achieved intelligence or super intelligence. It just means that Turing test has not aged well. For example, this is a screenshot from maybe 3 months ago. Someone asked ChatGPT, give me a sum of zero point 0.1 and zero point 0.2. It says zero point 0.3. Confidently, the user says you're wrong. It's zero point 0.3, 100 zeros, and then 4. And then it says you're right. It's zero point 0.3. And so it just agrees, and it's not really foolproof. So scientists are working on figuring out a better test to that. Couple years later, around 1955, the term AI was coined by Professor John McCarthy, who is considered to be the father of artificial intelligence. And then after 9 years, we had our first ever chatbot. So back then, before ChatGPT ever existed, there was something called Eliza, and that's Joseph Weizenbaum at MIT apparently interacting with Eliza, talking something around, "Hey, I'm really tired today." And Eliza replies, "Is it because you are really tired today that you came to me?" If you see what it is doing, basically is just using the words and reframing a response. So it could have just said, I am hungry. It would have said, is it because you are hungry that you came to me? So it's trying to just find patterns and being clever about it. So it's not really sophisticated, and it's just some rules trying to match some patterns, and we'll give a name to it in a bit. That's the algorithm. Read an input, find a pattern that matches this input, transform that input into a response cleverly, and make it feel like you are a psychotherapist. Again, fast forwarding, we had an AI winter around 70s and 80s. So a lot of money was put into this field, but not much value came out of it. And not so long later, around 97, there was Deep Blue, this algorithm, AI algorithm, which beats Yes, which beats the chess champion Gary Kasparov. What is Deep Blue? Deep Blue is basically it comes from game theory, which is again it has overlaps with artificial intelligence. So the name of the algorithm is minimax search with alpha beta pruning. Feel free to Google that. And this algorithm basically beats the then chess champion, which again uh, piques curiosity within everyone around what AI can do. Going back to chatbots, in 2011, Apple releases Siri, which I'm sure everyone knows about and how cheeky it was back then. Um, that's the that's a patent from Apple in 2011, showcasing what they had done back then to build Siri. It was nowhere close to what ChatGPT is today. It was again a lot of rules, but done in a much more robust and sophisticated manner. Still quite cool. Microsoft, by the way, also attempted to build a chatbot called Tay. It was a nightmare. I don't know if you guys remember, it interacted with people online and it ended up supporting genocide somehow. Uh, it basically learned all the abusive behaviors from people online. So that's the dark side of AI. From my perspective, one of the serious moments when AI really became something really serious to consider was AlphaGo. So Google's DeepMind, today Google's DeepMind, back then DeepMind, invented an algorithm called AlphaGo, which beat the then Go champion. Just to compare Go with chess, in chess you have 20 possible moves in one particular setting. In Go you have 361. So it's several orders of magnitudes more complicated to handle. And this was done with a much more sophisticated algorithm. Again, we will come to that in a bit. It's not the same as the chess algorithm. That's your timeline. I know we haven't covered all the recent developments, but I will again give a shout out to the developments from Deep Blue to AlphaGo, 20 years exponential improvements, and from 64 to 2011, from ELIZA to Siri, significant improvements, and also from 2011 to 2022, ChatGPT. You all know that how seriously impressive that has been. Cool. Going from the history slash timeline of AI, I want to also tell you about the fact that AI is not just one discipline. It has a lot of disciplines around it, which most people don't consider today because they're just focusing on that one particular branch. So starting off with something called expert systems, and I spoke about ELIZA, where it looks at your sentence. So what it does is you have a rule engine which looks at a pattern and replies cleverly with some words around that same word that you have entered to make it look like it understood you, but it's just some rules. And there is an expert sitting behind who is either updating those rules or adding more rules on top of that. So these were called expert systems. They're still used at many places. Still, some websites have chatbots, which are very primitive. If you enter something, they look at some rules and which category your question belongs to, blah, blah, blah. So that's expert systems. Then you have fuzzy logic. The idea behind fuzzy logic is humans, while computers believe in binary logic 0 and 1, humans have gray areas. So if I were to ask you, do you want to go for a game of tennis tomorrow? So your answer might not be 0 or 1, like yes and no. You will have a gradation between maybe, I'm quite sure, but let me see. So fuzzy logic captured that, and one of the examples of real life use of fuzzy logic was designing of traffic signal coordination. So if you have a main highway and then you have a side road, so if the highway is really clogged, the traffic signals on the main highway would be more green than red, so as to balance out And this involves relying on all shades of probabilities and not just zeros and ones. So that's fuzzy logic for you. There is something called evolutionary search. What happens here is you populate some data points initially, and then you have a scoring function to calculate which of these are the best data points. You take the best performing data points, you let them reproduce within themselves, you let them mutate. So imagine your data points look like vectors of 8 numbers. You let them reproduce and mutate. So what that means is they exchange some entries of their attributes, producing children who have mixture of attributes, and then they go back to the same scoring algorithm. So in this way, you tend to get the best data points out of what you started off with. An example of that has been drug discovery. So if you think about, you have so many complex compounds and you want to figure out even better compounds that can help with more precise and more accurate medicine. And this was used, or this has been used as classical evolutionary algorithms or genetic programming, as they say. Then there is game theory. Game theory is a huge discipline in itself. I'm not saying it's a branch of AI, has a huge overlap though with AI. And going back to the example of chess, I'll give you a reference on Prisoner's Dilemma. Please look it up if you're interested. It's a very interesting branch in itself, but the chess algorithm basically is driven by something along the lines of a minimax search, which says to minimize the maximum number of chances to lose. It's complicated, not in the scope of this presentation, but that's game theory for you. To also just give a sneak peek on two more branches. One is natural language processing. This is not from machine learning, but before machine learning, there have been attempts to understand language. So some things like stemming or lemmatization, you have one word expressed in different ways, and there have been attempts to find the base word, because then you can use that intelligence to write more rules. Like if you're asking Eliza the same word in different ways, it would be able to use this stemming or lemmatization to, you know, clean up that sentence and then process accordingly. Similarly, computer vision has existed long before machine learning. What you're seeing here is a photo of a cat, and then you are seeing a lot of lines. What has been happening there is something called edge detection, classical edge detection. So what that looks like is you have these two, what we call as convolutional kernels. They go around the entire image. So this one goes from left to right throughout the image, and this one goes from top to bottom, and they are multiplied with the pixels of the image. So it's a weighted sum on those 9 pixels in that neighborhood. So as you can see, these values, they kind of try to find areas where there have been a sharp deviation from the left to right. That's why you are seeing those points as highlighted to be of high value. Similarly, the vertical filter is trying to highlight edges from top to bottom. So basically, it helps you find edges. Granted, you are finding too many edges here because the cat has a complicated texture. And today, with more sophisticated technology, we can find a cleaner edge detection approach compared to this. So that's computer vision. And now, elephant in the room, machine learning. When we say AI today, we are basically talking about machine learning. I'll tell you why. Because all the different kinds of AI paradigms we have discussed so far, they relied somewhat on rules and somewhat on our expertise of the domain. But what machine learning tells, and the key word here is data, it basically is a paradigm where algorithms can learn functions purely from the data. So you don't have to go and explicitly teach it any rules, writing if this, then that, else this, and so on. And that was a game changer, I would say, since the last 2 decades. Within machine learning, you have 3 categories. Well, you have actually 5. I have kept them here in asterisks. I'm not going to go in details, but just to cover off, just to give you a teaser on these two. So it's supervised, unsupervised, reinforcement, semi-supervised, and self-supervised. Self-supervised is the recipe behind ChatGPT. It says that the machine learning model learns from patterns within the data. You don't need to give labels explicitly. I'll leave it at that, and I'll go back to supervised, which is the most classic paradigm of machine learning, where you give data with labels to this black box, this model. Here in this example, the data is images of animals. Labels are twofold, cats or dogs. So we have images and the labels cats or dogs. given to this black box, and this black box has some parameters inside it, which basically are tuned, and that's called training the model. In the end, when you send a picture of an animal to this black box, it learns how to classify that to a dog or a cat. Now, if you picture this, how would you do this with just software engineering or just writing some lines of code? It's quite difficult because how would you encapsulate how a nose of a dog looks different than the nose of a cat and so on? So it's easier to just throw in all data and let this model detect those nuanced differences. Then you have unsupervised learning. The key difference is that there are no labels here. So you can see that you again have pictures of cats and dogs, but you don't have the knowledge about whether it's a cat or a dog. Such a model typically classifies things into groups, abstract groups, and then it's for you to figure out what those groups are. In this case, those groups apparently are cats and dogs in the end, but this happens a lot of times when we don't have labeled data, but we still want to do something with that data. So this example is called clustering. We are trying to find clusters of data in this example. So imagine employees at XYZ. Just by looking at how they are talking to each other, you would be able to say if they're from marketing. So Adam is really like extrovert, talkative. You would know that he's from marketing. Ashish, not so much. Tech. So that's clustering. And oh, he's an outlier on the extrovert side. And then we have reinforcement learning. Reinforcement learning is a slightly different paradigm where we don't have labels for each instance of data. And instead, we have a game-like setup where you take a lot of steps, and only after the end of what we call an episode, you come to know whether you were right or wrong. So this is an example of this video game called Pong. On the right, you have this AI agent. At each change of frame, it's basically looking at the entire scenario where the ball is, where that player is, the other side, and it's deciding whether to move up or down or not move. By doing all of that through episodes and episodes, maybe millions of episodes, it's basically taught to, it's basically rewarded at each episode per win or lose of a point, and it figures out after each episode how to tune its parameters internally to make the right decisions. This powers this alone powers autonomous driving. So in driving, you can't, for each instance, tell someone, now you're right, now you're wrong. So you let them drive and then you tell them at the end you did well. So you are encouraging them. So that's positive reinforcement. And the other way around is negative reinforcement. And by the way, AlphaGo was based on reinforcement learning. This was also a model that really boomed the field of reinforcement learning itself. Coming back to machine learning being a branch of artificial intelligence which has eaten up the branch, the full picture actually is deep learning being a branch within machine learning which has eaten up the branch of machine learning and has eaten up the branch of artificial intelligence. So I correct myself. When you say AI today, 99% of the times you are talking about deep learning. What is deep learning? Two key differences. First is you are reading here vast amounts of data, which means suddenly we have a class of models which can leverage more and more data. And guess what? We have been generating more and more data. So it has the potential to unlock more value than the classical machine learning models. And the second thing that you will see here is neural networks. And the term neural essentially comes from neurons. So the idea behind deep learning or deep neural networks came from neuron. This is a neuron where you have some dendrites on the head, which are basically receptors for getting information from a previous neuron. Then you have an axon that transforms the information and sends that information to the next neuron in our brain, apparently. We use that as inspiration to build a mathematical framework where you have these dendrites like inputs with some values, and then you have what we call as weights or parameters. These are simply numbers that get multiplied to these input numbers. So it's a weighted sum basically of all of this coming around to this value z. And then from z, we have an activation function applied. What is an activation function? It's a nonlinearity. Why do we need to add nonlinearity? A bit of linear algebra, if you have just a bunch of linear functions next to each other, even if you stack hundreds of them, they would collapse into just one. So if you need to add nonlinearity to make them complicated enough. So this basically makes them powerful, makes them more complicated, makes them capable of learning more complex patterns. Now, when we say deep neural networks or deep learning, that term deep comes from doing the same thing over and over again. So this block is all of these blue dots here. and each of them are neurons, and they're connected in a dense manner. And this is called a deep neural network. You have inputs, you have hidden layers, and you have output. So actually, the branch is called neural networks, the branch within machine learning. But when you have too many hidden layers inside, more than two, it becomes deep learning. The term deep comes from too many hidden layers in between. An example, let's say you have an image of a handwritten digit. In this example, that handwritten digit is 3. This image is 28 by 28 pixels. Okay. If I take all of them pixels, which is a total of 784 pixels, and list them down as numbers between 0 and 1, and pass them as input to a neural network, and there are multiple layers ahead of it, what happens is I initialize those parameters, those wires with the values randomly. And then I expect in the end 10 kinds of outputs corresponding to 10 classes, 10 digits. I know that this is digit 3. I have that label of 3. So I expect this to be lit up the most or this to have the highest value, but it doesn't. So I find out an error function basically to represent that gap and use that gap to back propagate throughout the model to teach the model, hey, you're making a mistake. Try to correct yourself. Try to tune your parameters, all of your parameters somehow. I don't know how. It's like Dave coming back to us. This is not working, guys. Figure out. And then Jack goes, figures something on Jira. Tom goes, builds something on the product roadmap, and so on. So we have a structure. Similarly, here we have this overall overarching back propagation system, which tells the model parameters to tune themselves. And this process is called training of a machine learning model. Now, that's one example of a neural network architecture. There are many neural network architectures available today in this world. This includes convolutional nets, recurrent nets, and transformers. Transformers being the current buzz and hype. So they are the transformers are the architecture that underlie ChatGPT, Stable Diffusion, all of these latest models that you see around yourself. And guess what? We have PyTorch and TensorFlow, some of those frameworks that basically abstract out all of those details and enable people like me and Ahmed and Will to write down that code to train these models very easily. And then we also have books, some notable books that help you. Yes, let's talk about that after the lunch and learn. So, and then you have books around that, not just my book, but many books around this to help you learn how to use these frameworks, basically to be able to code these neural networks very easily. Two quick shout outs before I go to the next section. Machine learning and deep learning also differ insanely in the sense of in machine learning, I have to hand engineer features. Imagine spam classification from emails. I will have to hand engineer things like, are there more than X number of spelling mistakes? Are there more than Y number of punctuation marks? Are there more than blah, blah, blah? You know, all those individual rules that I have to write down, and those numerical values go to a machine learning algorithm. As opposed to that, for a deep learning system, I'll just shove the entire text of the spam email into the system, just like I shoved the entire image into the deep learning system. This is also why deep learning is incredibly lucrative. The second shout out is about many of you will go after this talk and then say, why didn't he talk about generative AI and LLMs? The full picture is this. You have AI, you have ML eating up AI, you have neural nets overshadowing the entire field of ML, deep learning, which is deep neural networks. And within deep learning, you have generative AI, which are these new models that came up and then caused all the buzz. And then within Gen AI, you have LLMs, because there are also other Gen AIs like Stable Diffusion, Midjourney. There are also Gen AIs, but they're not LLMs. This picture is still not 100% correct, but this still captures, I would say, 95 to 99% of truth of today's AI world. Now, I want to show you something useful, like how do we, all of that is fine. This is theory, this is literature, but how do we work, me, Ahmad, Will, how do we work on AI stuff? And so there are three parts to performing anything around AI. One is training, one is testing, and one is inference. And I'm going to use some analogy which hopefully resonates with everyone. Training is much like teaching a bunch of students in a classroom throughout the semester. Testing is like the exam day where you have taught something to the students, they have learned something hopefully, and then they have a question paper, they have to write the answers, and then they get the marks. If they pass, if they graduate, they go on, they get a job, and then they, do wonders with their jobs. So those are the three stages, right? Just keep them in mind. And to to complete the picture of analogy, data scientist in this case is the teacher who is trying to teach the model, who is the student, the AI model turned professional in that picture. And the textbook is the labeled data. So that's the resource that the data scientist is using to teach from. Which brings me to the final section of this talk, which is AI at XYZ. I'm going to use package predictor, which Ahmed has spoken about quite a lot of times. And I'll use the same framework. So let's start with training. We have our data scientist, in this case, Ahmed, who is the teacher from the analogy. We have our label data. I couldn't find a better way of representing label data, but Mustafa, who gives us all of that information between activity names and the packages, he's our textbook. And then we have package predictor, the AI model, which is the student in this case. Now, all of this is symbolic, right? Let's make it more concrete. The real equivalents are, we have something called a BERT model. It's a transformer model. As you can see, this module, which has two layers, is 12x, which means it has 24 layers, and it has a total of 110 million parameters. Just imagine that. This is tiny compared to today's chat GPTs, which are like trillion parameters in size. Um, and to make Ahmed's role more concrete, he uses PyTorch, I suppose. He writes some code which loads this BERT model from some libraries using Torch, and he's ready to use that label data from Mustafa. And now he's waiting for Mustafa to give the label data. How does that look like? It basically is the text for schedule activity, and then the equivalent categories for schedule packages. This is the real setup that we work with to build package predictor. And to show you how it trains really. So you can still picture this in your mind, and instead of the image of a digit, you have these texts laid out as numbers. We won't get into that level of detail. And it goes through this entire model, produces one of these, let's say 10 categories. And it was supposed to produce containment, but it is saying electrical support. And so Ahmed figures out a way, an error function, which helps the model train, learn from these errors. And eventually, after several what we call epochs, or several times of looking at the entire data set, the model has tuned all of its 110 million parameters in a way where now it's ready. Give it a schedule activity name, and it's going to produce with 90 or 95 or 99% accuracy the correct package. And keep in mind, it will still output probabilities. So it's still going to be in the continuous domain, and then we use a threshold to convert that into a concrete decision. So testing looks very similar because the teacher who is teaching the students uses the same syllabus to build a question paper from. Similarly, Ahmed uses this same data set and takes a slice out of it, keeping it for testing. And so he just uses a similar PyTorch code, I assume, to perform the testing and gets some metrics. And finally, the third part is inference. The model has been trained, it's graduated, it's ready to get a job. And so what happens there is, again, Ahmed uses PyTorch still to write a service code where it takes the trained model object, has some PyTorch code, which basically loads the model and is ready to service. But where does it live? And this is where I'll just complete the analogy, might be going too far, but this is where the cloud team comes into play. And in the analogy, he is the job center plus. So if our graduate is struggling to find a job, Joao is here to help them find a job, which is to place them in the cloud, which brings me to the end of my presentation. Thank you. And now, before I take questions, just one final thing. So we did a survey, and we only a few responses came up. So I have to say again, please interact with us. We are not AI, we are building AI. So please be free to take part in those surveys. It's really valuable for us to get some feedback from you. We want to work together with the teams and not just like in a silo. But nonetheless, from all the responses we got, I have my two lucky winners to get these two copies of the book in front of me today. And they are Dave and Masoom. So congrats, guys. And next questions, yeah. It has to be live so that they see it. So I was waiting for sure.
Some of you guys don't know my past, but I used to work with a lot of machine learning experts building machine learning systems for them. I understand no machine learning, nothing, but they used to tell us that they had 100 parameters to train. You show there that BERT has 110,000 million parameters. How much more computational needs expanded? From someone that manages machines to you used to ask, I don't know, 20 cores is fine. Are you going to ask now 200,000 cores to train? How does it actually calculate the... Yes.
So amazing question. Yes, we will be seeing more and more heavy models coming up more and more. So there is a whole discipline within AI called ML ops, where we deal with this problem of trying to optimally use models. First thing is the requirements on the hardware do not scale linearly because the architectures are not like just linearly stacking on top of each other. There are more parallel units and so on. There are memory requirements, so it holds up a lot of space in the machine, but there are also CPU requirements, so it needs a lot more cores. It is definitely a question that needs a separate maybe 10-20 minutes of discussion to give you the picture. But at our side, we will always be sure to use the minimal amount of parameters that does the job. So be it through, I'm just going to say some words, quantization of ML models, be it through distillation, pruning, these are the ML techniques, or be it just through using a simpler model for a task. So some of our tasks don't need ChatGPT, but some of them do. And we will have to figure this out. For extremely heavy models, which are LLMs, there is a huge discipline now called LLM ops, which deals with even more fine-grained hardware optimization. So this is really cutting edge today. We have, I mean, it's very difficult to answer all of that here in this session.
Yeah, you could take it back again. It's about foundation models, so LLMs, and I hear talked about that actually a lot of the foundation models like GPT-4 or I guess BERT or others, they're starting to achieve a level of performance that actually exceeds the threshold for a lot of use cases. What's your take on whether we are actually reaching a point where there's increasingly no need to custom train models because the foundation models are so performant, particularly in our context for construction?
The trade-off there, so foundation models are great. Thank you. Foundation models are great, but the trade-off that we see right now today is the small language models, SLMs, are more impactful so it's about the bang for the buck. So the foundation models are too heavy to maintain and host. They might be trained on a lot of different data and maybe a little construction data. What we want at XYZ is just maximal performance on construction data. So while we still want a model to sound like a human being and so on, we want to fine tune a lean model, a smaller model to our use case. So, and this is a practice. There is a Y Combinator article that came out maybe a month ago, which says in the recent cohort, 70+% of their admissions, the startups, they are basically not using the large language models, but they're fine tuning the small language models to their use cases, because that's apparently more than enough to give them enough accuracy in their domain. So if we want to restrict within construction, I think that's the way to go. Having said that, the large language models can still serve offline as experts. So as a proxy for a human, because they have much more wider knowledge about things.
So I read somewhere that it cost ChatGPT $100 million to train up ChatGPT 4 on compute costs and stuff. Do you know any more information that if that was how much it cost or what it covered?
I'm not surprised. I know OpenAI never revealed for ChatGPT 4, GPT-4 at least, but for GPT-3 it was already double-digit $1 million. I'm not surprised because, firstly, we are talking about when we say foundation models, we are speaking about training from scratch. So if you remember those weights or parameters, imagine a trillion of them starting from random values. And now going through epochs and epochs of looking at the data set. And what's the data set? The data set itself is in double digits of trillions of words and across the entire text corpus, across Reddit, Wikipedia, and so on. So to look through all of that, it's one epoch. And these models usually are trained for at least tens of thousands of epochs. Now, this also means you have to load this 1 trillion plus parameter model into a device, which you don't, right? You shard them across several GPUs, multi GPU clusters. So just keeping in mind that the rent of one useful GPU of this class for a month is around $1,000, the minimum, just one GPU, and they have to use at least hundreds of them just to support this. So that alone should give you an idea of just our daily cost. Sounds in the range of tens of thousands of dollars, and if it goes along for months, which it does, then that quickly catches up. Any other questions? Maybe on the call? No, if no further, is there something? Okay. So, so the question is, how much energy is consumed in training an AI system? Will it be a problem in the future as systems become more advanced? Um, Another great question. I keep reading about this as a concern, given the climate crisis as well. Yes, we are in a high cycle of training LLMs. Like it's a race right now within companies, and yes, in the crude manner, people are just using a lot of energy, suboptimally so. So there's a lot of startups coming up in this space of building more hardware that is geared towards training ML or LLMs. But right now, it is a concern. I think still the good news for us is we have a lot of opportunity to build more data centers, and it's for them to use the most cutting edge hardware within those data centers to enable like maximal use of computational power for the electric power that it consumes. But yeah, that's a real concern as of now. Cool. Thank you so much for joining, everyone. I hope you enjoyed it. Hope you liked it. We'll, we'll try to do a series of this to go more into the depths of other subtopics, but that's it for now. Thank you.